This computer.
Diagonal.
Nice.
So the tutor and then having.
Oh no, just your email.
Your hi. Oh. And also talk to you. Okay.
Needs to like something that has like a single non-zero down. But you can.
Just
You don't have like.
yeah, it's okay. Yeah, I thought it was a. It's from that guy. Yeah.
We're one, two different pages, right? Or not having, but you know, also two different nine.
Okay, who started? Yeah, welcome to a private seminar. Today our speaker is Yuehaw Khoo from the from the University of Chicago. Yeah.
Okay. Yeah. Thanks a lot for the invitation. It's I'll say it's really my honor to be here and speak to you guys. So today I'll talk about convex relaxations for many-body physics. Okay, so this is the roadmap for today's talk. First, I'll talk about how to use convex relaxation to solve high-dimensional PDE in statistical physics. Part two will be consisting of like solving high-dimensional eigenvalue problem in quantum physics. The difficulty of these problems lie in the fact that they suffer from the curse of dimensionality. And the theme of today's talks will be, we're going to try to modify sum of squares method to handle this type of situations. All right, so before talking about the problems that we're interested in, let me first talk about what is the sum of squares method. So this type of methods arise in the context of optimization. So you want to solve a global optimization problem. You're given some potential u, right? Like, and this is a function that is supported on RD. So this is like a high-dimensional function. You're thinking like D is large. Okay. So the difficulty of solving this problem is that usually this function u is non-convex. So it's hard to find the minimizer x star. Okay. However, people realize that this problem can be recasted in a measure optimization problem. Say you take your function u and you convolve with a measure mu, right? And then you impose some constraints that, well, this is a measure, like mu has to be non-negative and it has to integrate to 1, like conservation of mass. And you mean over mu, okay? Well, if you just eyeball it for a moment, you realize that the minimizer of this minimization problem is really a Dirac delta situated at your minimizer x star, okay? Right, so all the mass will go to that 1 point x star, okay, if there's a unique minimizer. Now, well, if you change your perspective from the first problem to the second problem, you get a linear problem. Just that, well, now you pay the price of the curse of dimensionality. Okay, so the size of this measure, right? If you have a measure in d-dimensional space, you're gonna run into exponential cost in the dimensionality. Okay. Well, you go from non-convex, right, to a linear problem. Just that this linear problem is too big. Okay. Right. So now then you do another reduction. Okay. So instead of looking at the entirety of the measure, you write the problem in terms of the moments of mu. So let's say you define this moment matrix. So x alpha, x beta, these are monomials, right? So alpha is a multi-index. Now you take this x alpha times x beta, and then you take expectation with respect to mu. Now this becomes a moment matrix. Okay. In this way, right, you can rewrite the problem in terms of the moments. So suppose the cost function is actually a polynomial, right? So ux, right, takes the form of sum of a bunch of monomials. So the cost function, right, once you integrate it u against mu, you can write it as a linear problem in terms of the moments. And the equality constraints can be dealt with similarly, right? Integrating mu equals to 1 is really just a linear constraint on the 0, 0 elements of the moment matrix. Okay, so well, then you have the last difficult one. Okay, the half space constraint mu is non-negative. Well, to handle this, you only enforce some necessary conditions that it has to be non-negative. So the way to do it is really use it through a weak formulation. You pick some non-negative function, q, you integrate against mu, and you ask for the results of this integration to be non-negative for some selected q, okay? The standard choice of q, right, what kind of q is really the sum of squares polynomial. So this space, calligraphic q is the convex hull of the square polynomials. So it turns out there's an efficient characterization of this type of constraint, right? You're taking mu and you test it against some non-negative test function q. This is really equivalent to saying the moment matrix M is positive semi-definite. Okay, so you can see it easily. I'm going to provide you a quick derivation. So say you have some function f, right? You expand it in terms of some monomial basis. Now, if you take the square of the function and you test it against the measure mu, right? So I'm going to substitute this into my function f. It's going to look like this. Okay, so you sum over alpha beta, and then you have your moment matrix show up over here. So now you have a bilinear form in terms of the coefficients of this expansion. So if you ask for the results of this test to be non-negative, it's equivalent to saying this moment matrix has to be positive semi-definite. Now, to summarize, you change a global optimization problem to a linear problem in terms of the measure, then you relax it, okay, to a linear problem in terms of the moments. Here, when I say relaxation, I mean that you have this inequality, okay? So the reason is the following. You didn't enforce all the constraints that the measure has to be non-negative. You only enforce some necessary conditions. So the set of optimizations becomes larger, okay? So hence, the minimum is lower. Okay, so this type of approach are basically developed in these two papers, okay? There are many advantages to this, right? That is convex, there's no local minima issue, and often the lower bound is tight. So there are many successful applications in the last 20 years of applied math, and has been one of the pioneer of this type of methods, convex optimization, compressive sensing.
I avoided convex.
That's true. Yeah, yeah, that's right. Okay, that's true. Right. Grid is good. Yes, that's right. Local optimization is better. Okay. All right. Okay. Yeah. Sorry, I misrepresented your stance on this issue. Yeah.
Forget
right.
stuff. We'll do those really big
Convex.
Convex constraint.
Yeah.
Yeah.
All right. At least I get one part correct. Okay. Okay. All right. So so now I'm asking the questions like whether this can be applied to other measure problems. Are there other opportunities for this type of method? Okay, so today the part one of the talk will be a statistical mechanics application. I'm going to talk about convex relaxation for Fokker-Plot. So let's look at a more general form of the energy minimization problem. Okay, so again, you have this term, right, which is minimizing the energy, and you have an entropy term. Okay, right. So T is the temperature. In this case, we know that the solution, right, mu star looks like this, right? Is the Gibbs measure divided by a constant z. Okay, right. So basically, we kind of know the solution, except we don't know the constant z. And turns out the difficulty lies in how to find this constant z. This kind of like strictly generalized the global minimization problem by including the temperature effect. However, for this type of problem, it's actually harder to apply the idea of sum of squares method because the problem is no longer linear in the measure mu, right? So as you can see, all the reduction that I have just now are conditioned on this fact. Okay, So now let us look at a different characterization of the equilibrium measure mu star. Okay, so let's think about like minimization problem as performing some gradient dynamics. Okay, so let's look at the Langevin dynamics. I'm minimizing, right, the potential through a gradient dynamics plus white noise. Okay, so T is the temperature and the white noise scales with respect to the square root of the temperature. So this is like the overdamped Langevin dynamics. Now, the law of xt, right, let's say mu t, satisfies the Fokker-Planck equation. So here you have the diffusion term, right, again, controlled by the temperature. And then now you have this transport term, right, like where the drift is governed by the gradient dynamics, okay. Again, this is a high dimensional problem because mu t is a measure in a d-dimensional space. Well, the stationary solution, right, L mu equals to 0, in fact, gives you the equilibrium measure mu star, okay. So, okay, all right. So, how do we solve this equation? Okay, we kind of like get a linear characterization of the equilibrium measure, right? Mu star in like in the form of a PDE. However, it's still difficult to solve it, right? Like because a mu has an exponential size in terms of the dimensionality d. So the first fortunate situation is that typically most interaction that we know of, right, U, right, actually takes this form, Uij, Xi, Xj. So for example, the gravity, right, like for example, Coulombic potential, they all look like a pairwise interaction. So we're gonna, for the rest of the talk, I'm gonna assume the interaction is pairwise in nature. Well, once you have this assumption on U, what people typically do to solve this high dimensional equation is through a mean field approximation. Okay, so to summarize, what you do is the following. You take this equation L mu, right? You integrate out all variables but the ith variables. You leave out one variable, but you integrate everything out. Now you're left with a one-body operator acting on mu I. So mu I, I'm going to use to denote the ith marginal, right? And mu ij is the ij pair marginal, okay? So this equation, after this integration, becomes a one-body operator acting on mu I and a two-body operator acting on mu ij. So without telling you what's going on over here, I'm going to tell you what the physical meaning of this. This is really saying, right, let's say if I fix a particle I, right, this is calculating the total force, the average force of j particle acting on I particle. Look at this summation over j, okay? Right, so, okay, so now you have an equation in terms of mu I and mu ij. Then the next step, right, in order to derive a closed equation, is to split this mu ij into mu I times mu j, okay? So this is something, well, you can think about this as decorrelation. You have two marginals mu ij, right? You think about the I variable and the j variable as being independent of each other, and you decorrelate mu I into mu I times mu j, okay? So this actually gives you a nonlinear equations, a set of nonlinear equations, right? You have B equations over here with OD parameters, right? Because you just need to handle mu I, right? I from 1 to D, okay? Right, that's the kind of like the standard way. So if you think about this procedure, what you're doing is the following. You take your mu, right? You split it into a product measure, okay? So you decorrelate the measure. And then that amounts to restricting the solution to a non-convex subset of the probability simplex, right? Some very low dimensional manifold, okay? Right. Well, we're going to take a different type of approach, okay, that comes from the philosophy of sum of squares method. We're going to instead relax the probability syntax to a larger convex set using the way I just talked about. So you can look at the weak formulation, right? You're going to test your Fokker-Planck equation, right, with some test function t, right? And then you move L right to the other side with the adjoint operator. Now this again becomes some moments system, right? For the measure mu. You're gonna pick some t. Okay, I'm gonna tell you what that choice is. Now again, you're gonna test the non-negativity constraint by taking some non-negative q and integrate again the measure and ask for a test to be non-negative again for some choice of q. And then you're gonna say that there's a conservation of mass. Okay. Right. So now the number of non-negative constraints, if you think about it, right? originally you need to enforce non-negativity over the entire space. Now I select some functions to enforce the non-negativity. So in some sense, the number of constraints drop from this exponential size constraint to poly depending on what kind of test functions I pick. So here's the choice that is drastically different from the previous sum of squares approach. We're going to choose our test function T to be coming from the span of a cluster basis, okay? And Q coming from square of some function. Again, this function S is coming from span of some cluster basis. And I'll tell you what this means, right? So if you have a K cluster basis, it means that these functions, right, are some K variable functions. For example, if you have one cluster basis, right, it looks like this. So I have basis, I have single variable basis, and I'm enumerating through the dimension I, right, different variable I, and each dimension I have n basis, okay, right? So these are all single variable functions. So like I said, this is different from traditional sum of squares with a low degree monomial. So like Peyton and Rafi, we have a discussion this morning. So the traditional sum of squares method, like based on low degree monomial, is essentially assuming your dual test function is smooth. Okay, and once you make that assumption to approximate that space, you immediately suffer from the curse of dimensionality. So you have to move away from that in order to gain like a polynomial time algorithm, okay, in the dimension. Okay, so I'm gonna run through this example. I'm gonna choose T and S, right, to be K equals to one cluster basis, single variable function. Okay, so yeah, there's some derivation right behind, but if you make this choice, essentially, it's equivalent to saying that I want to solve this equation, right? This is the equation that you see before, but now I have mu ij, okay, instead of mu I times mu j, okay, I have mu ij. So I didn't make any independence assumption, but I have a long list of constraints to constrain mu ij, okay? So for example, there's a non-negative constraint, like I said, I have these single variable functions, I sum them, I square them, I test it against mu, I ask it to be non-negative. Just like before, there's a positive semi-definite matrix that comes out. This is equivalent to some positive semi-definite constraint, right? Because again, like you run through that bilinear form and then you're gonna see that, okay? So you have this matrix G, you have this one marginal stacked on the diagonal, and you have these two marginals on the off diagonals, okay? And then this guy is positive semi-definite. Yeah, of course, I abused the notation a little bit, right? So I really should say that this guy is positive definite with a suitable discretization of the space, of the single variable space. Okay. Then there's some obvious constraint, like for example, local consistency. The marginal of the two marginals should be the one marginals. Okay, these are kind of obvious. And then mu ij has to be non-negative. Okay. Then you also have the normalizing constraint, right? Each mu I integrate with one has to be one. So these are the full set of constraints. So again, to summarize, instead of applying this correlation, mu ij equals to mu I times mu j, I have all these constraints, okay, that is characterizing my mu ij. So this gives a linear semi-definite program of size nd by nd. N is the number of discretization per dimension, and d is the dimensionality, okay? So, but you're gonna ask the question, right? I have d equations. Basically, I have one equation per marginal, okay? But I have all these square variables. So it doesn't seem like I have enough equations to determine the variables in the optimization. So, well, now you ought to feel like maybe, right, perhaps all this complicated set of constraints work in a way such that the space of optimization is actually not quadratic, okay? So the constraints are providing sufficient, like I don't know, like a sufficient constraint. Yeah, that's right, regularization on the space, right? Exactly, thanks, yeah. So here are some theoretical results, right? So let mu star be the ground truth Fokker-Hahn equation, and mu I star be the ground truth ith marginal. So I'm trying to show that whatever we recover will be close to the ground truth ith marginal. Okay. So I'm gonna make a few standard assumptions and a few non-standard ones. The first one is really the existence of the mean field approximation. So I'm gonna suppose my ground truth mu star is already eta 1 close to a mean field. Okay, right. So right, like basically, if I want to find a mean field approximation, I better hope there exists one. Okay, that's the question of existence. Now the second one is coercivity is really the analog of strong convexity in function space. We are saying that this bilinear form, right, ULU, right, is actually going to be lower bounded. So the second eigen value of this this bilinear form, right, is going to be lower bounded by lambda. Okay. So this is ensuring the uniqueness of the Fokker-Planck solution. Okay. The third one is a little bit non-standard. Okay, the third one is kind of like assuming what I want to prove. Okay, so I'm gonna assume that, right, summation, right, of the force. So I'm fixing the particle I, right. So this is the summation of all the forces acting on I, is gonna behave like a mean field. So this force, right, is just gonna be the same as this guy, right, in eta 2 sense. Okay, it's gonna be eta 2 close. Okay. All right, so again, I'm assuming what I want to prove. Okay. All right. So, but say you agree with me on these 3 assumptions, you're gonna get a perturbation bound. So in terms of chi-square divergence, mu I is gonna deviate from mu I star, right, by this amount. So this is really just perturbation analysis. Okay. So there's a spectral depth, and these are the perturbations. Okay. All right. So you're gonna ask, right, what kind of systems satisfy this assumption? Again, 1 and 2 is kind of standard. Okay, the third one is really non-standard. Okay, so I'm saying that, okay, some arbitrary measure mu ij that satisfy my convex constraints is gonna look like, mu I times mu j in the sense of the force it acts on I. Okay. All right, so well, actually, this is really the soft part of the talk. I must admit, I don't have a great understanding, but I can provide you an example showing that why this could be true. Okay, so say you have so let's come back and study what these operators are. So the single body operator Li is actually just the one side diffusion term, right, acting on the ith margin of mu I. So the two body term Lij mu ij is looking like this transport term. So what you can see is the following, right? Here I have an integration of mu ij against the force uij. This is averaging, right, the forces from the jth particle acting on the ith particle. Okay, so that's what this is doing. Okay, so if we start with a simple situation, if uij in fact looks separable, fi xi plus fj xj, it will satisfy assumption 3. Okay. Again, this is super. I'm starting simple. Okay. In this case, right, if you look at this, I take the derivative with respect to I, it's gonna kill this second term. So this term is gonna be left with gradient of I, fi. Now I integrate out xj, I'm gonna be left with mu I gradient I fi. Okay. So basically what it's saying is following. Lij mu ij doesn't really depend on mu j at all. So Lij mu ij is actually equals to Lij mu I times mu j for any mu ij. Okay. But the natural question is that, is assumption 3 only true for a separable potential? Because if the potential is separable, you can apply separation of variables, which you learn from undergrad PDE, and then just solve each equation independently and call it a day. Okay. All right. So here's okay. Let's make it more difficult. Okay, you take this, right, and then you add a perturbation bij xi xj, which is non-separable to it. So I'm gonna assume fi is gonna be order 1, and this perturbation term bij is gonna be expanded in the single variable basis with some coefficient bij kl. Okay. And I'm gonna draw this bij kl from a normal distribution, right? 0 sigma squared. So you can think about this as like some random perturbation. So if the sigma is very large, this is actually non-separable. And of course, the question is like how large sigma can be, right? So actually, with this type of potential, you can calculate that eta 2, which is the third assumption, the deviation of the third assumption, is square root of v times sigma. Okay, so this really comes from like kind of like the singular value extremal singular value of a random matrix. Okay? And your spectral gap lambda is order D. So the error between mu I and mu I star is eta 2 divided by lambda, right? Is sigma divided by square root of D. So the non-separable bar can be really large. So it can be little o square of D. So in fact, the non-separable bar can grow with the dimension. And the main idea is really the following. Okay, so the noise part, right, which is the Bij, the noising part, is a random matrix. Okay. Now, let me assume that n is order 1. If that is the case, right, that basically the number of bases per dimension. If that is the case, if I try to max over Bij integrated of mu ij, and mu ij is restrained to be this like a complicated looking convex set, is actually order-wise the same as maximizing over a positive definite matrix where the trace of G is equals to D. And we know that this guy is a D times square root of D sigma. Okay, so again, D comes from this normalizing factor, trace G equals to D, and square root of D sigma is just the extremal value of the singular value of a random matrix. Then the signal part, right, because you have sum over this pairwise term Fi Fj, so it's going to be OD squared. So the signal, the noise to signal ratio is sigma divided by square root of D. So this is a kind of like a rough idea of the proof. So let me show you some numerical results. I'm going to use this kind of like a toy-ish one-dimensional interacting system to illustrate. So you have Ux, right? You have some interaction between nearest neighbor, so xi minus xj squared. So this is penalizing xi cannot be too different from xj. And then you have this xi, this quartic term is penalizing xi. Each xi has to be close to plus minus 1. So this is kind of like a continuous version of the Ising model. Okay, right. Again, it's the adjacent spin wants to be close to each other, and then xi squared, right, has to be kind of like plus minus 1. And then this lies on a 1D chain. So this is a chain graph. Okay. So I'm gonna work with a dimension 10 example, right? I'm gonna pick a certain choice of lambda. And then the temperature is 16. So for this, I'm getting about 2 digits accuracy in terms of the marginal distribution. Okay. Okay. So now let's look at a more difficult example. Okay, so in the previous example, each dimension wants to be close to each other. So in a sense, in physics, this is kind of like a ferromagnetic Ising model is actually kind of simple. So let's look at the repulsion. Okay, the repulsion cost. So let's say you have like so let's start with some Uij, xij, and it has a permutation symmetry. Basically, Uij, each of this Uij is actually equals to the same function due to that. Okay, so basically, I'm assuming, or you can think about it like as like gravity, okay, or like a Coulombic potential. So all particles interact in the same way as each other. So it turns out, right, because of the permutation symmetry, you can simplify this second marginal matrix dn by dn to n by n because all 2 marginals are the same. Now let me try to use this, right, to solve for the Coulombic potential in a box. And I'm gonna make it soft because I don't want to make my life too difficult in terms of discretizing the Coulombic kernel. They are like the grandmaster here, and yeah, happen to be not one of them. Let's say we are looking at this Coulombic potential, and then I softened it by adding like 0.1. Okay, and I put a box around it. Okay, so these are confining potential so that it doesn't leak out of the box. So I look at the case having 4 particles, right, and with certain choice of with 2 choice of temperature. Okay, so these are the 2 different results. You see 4 bumps because you have 4 particles in the box. Okay, so these are the locations. And as you can see, right, so the red curve, right, is our reconstructed marginal. The blue curve is the true 1 marginal. They only get qualitative agreement. So the 1 marginal distribution is 10 to the minus 1. So I suspect the loss of accuracy is due to the one of the assumptions not holding. I think mean field is in general a qualitatively good approximation for repulsive potential, but not a quantitative one. Okay.
Yeah. One stupid question. What are these graphs?
So I'm plotting the one marginal.
What does that mean?
So I put, so this is my box. The one marginal is like kind of like the marginal density of the electron. Okay, so basically it's gonna tell you how likely each electron is gonna be in what position. Okay, so
And that's the configuration for lowest energy.
so for the equilibrium distribution, yeah,
Configuration is-
yeah, that's right. In equilibrium, right, the 4 electrons kind of distribute like this. Okay. What time is it now? Sorry.
It's 3 o'clock, so we still have certain.
Oh, this is okay. Yeah.
How is your discretization? Like, how fine is your discretization? Does it get better with better discretization?
Yeah. So it does, but at some point, like the limitation is
Yeah.
really relaxation
And
error.
the limit is 10⁻⁻⁻⁻.
So yes, that's right. So actually for this, actually already, well, first I softened it so that I can discretize with like higher accuracy. And I'm already discretizing with like almost 200 points. So as you can see, it's reasonably smooth function. You should, yeah.
It doesn't get better.
It doesn't get better. Yeah.
And what about like different softening?
Oh yeah. So actually, if you don't soften it,
Or like higher or lower, like what if you tweak the 0.1?
yeah. So if it's okay, if it's high, if I lower it to 0, the results gets worse than this. And I don't know whether it's due to the fact that the interaction is stronger or the discretization error is not good. Like that's why I put this 0.1 in order to make sure I know what I'm doing. Yeah.
And what type of discretization do you use?
So here okay. So to discretize the marginals, I'm using like head functions. Yeah. Just local linear. Yeah. Yes.
Knowing neither the numerics nor the physics, what are there any other numerical techniques that can do this?
Solve the so the most typical one is the mean field method. You just basically this is right.
How you get 10⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻ possibly do?
I think from my experience, it's about the same as the mean field method.
Okay,
So there is a model. So this 10 to the minus 1 is really a model error. So I claim I want to solve the original PDE, but I make an approximation to the solution. And at that point, I commit an irrecoverable error. And
Right.
yeah,
and presumably this approximation allows you to do this so much faster than.
so I was,
Convex.
yeah, that's right. So I would say the main advantage is that it's convex. I know you might.
Okay, no, you have an answer.
Right. So yeah.
In finite time.
So right, like so basically once you know it's convex, right, it becomes a linear problem, right? So this type of if you want to solve this nonlinear equation, even let's just say even like a stability or well-postedness of the equation is questionable. I mean, like typically you could with Coulombic you could have only short time well-postedness. Yeah. Yeah, but I have a fully convex linear problem, yeah, which I guess is a little bit more stable.
Do the runtimes compare? For example, the mean field.
Oh, mean field is so fast. Okay, let me just put it this way. Mean field is very fast. Okay.
So if you are more accurate and it is a more expensive algorithm, so what is like the benefit then?
Oh, actually, mean field has a stability issue. If you're trying to solve it, yeah.
Okay,
right.
So this
So-
is more accurate.
Well, it's more so if mean field converge is super fast. Okay, right. That's right. Right. So the way to solve for this is like they call it a self-consistent iteration, right? Every time you solve for a mu, right, you fix this one guy and you solve another linear equation until it converge. I mean, like it bifurcates sometimes. Yeah.
And possible that this is amenable to other kinds of problems for which the field approximation calculation is no good.
Yes, and yes, and yes, exactly. Part two of my talk will be actually regarding that. Okay, yes, yeah. Well, part two of my talk will actually try to address the issue that it could be as fast as min, at least from a per iteration complexity point of view. Okay, could be. Okay, no guarantee. Okay. Right. I mean, yes, mean winding conversion is just very, very fast. Maybe in 5 or 6 iteration of this, like you just need 5 or 6 PD software to conversion. Yeah. I mean, in some sense, it's kind of like a Newton's method, right? You're locally linearizing the problem, and yeah. Okay, so to end this first part, right? Like I'm proposing like a hierarchy to solve this high-dimensional Fokker-Planck equation, right? You have some test function that you can test against, like you can choose from a set with more and more well, complex function class, and also right for testing the non-negativity. And we have also applied this to solve like a time-dependent Fokker-Planck equation, okay, which requires more bases, as you can imagine. Okay, so I haven't talked a lot about how to actually solve the problem. I'll tell you how to pose the problem as a moment problem. And what I did for those simulations is I plugged it into CVX package and solve for it. Okay, so it really can only solve a very small problem. Okay, right. But then like, let's say, okay, I solve a 10 particle problem or 4 particle problem. Let's say I want to solve like a 100 particles problem. How am I going to be able to solve it, right? Okay, so this is actually concerning this is what I'm going to talk about in the second part. But I'm going to use a different measure problem, right, to illustrate the idea. Okay. All right, so let's look at a quantum ground state problem, which is an analog of the statistical mechanics ground state problem. Okay. Say you have a d-body Hamiltonian H, right? It's a big matrix. Is like 2 to the power d by 2 to the power d matrix. And what you're looking for is the ground state wave function psi. Again, is a huge factor. Okay. So the ground state energy problem is really this naively and simple looking eigenvalue problem where you want to minimize this Rayleigh quotient. Okay. And with this normalizing constraint. So suppose your Hamiltonian H is really a diagonal operator. H is diagonal U. This boils down to the classical optimization problem. So in that case, right, like if it's a diagonal operator, then you have psi square, right? You have this psi square inner product with U, okay? And then you have this normalizing constraint. And then this is equivalent to integrating U with respect to the measure. And then the measure is non-negative and it has to be greater than 1, okay? So the quantum eigenvalue problem really generalized the last year measure optimization problem. Well, but then the bad news is that this requires H to be a diagonal matrix. So if H is just a general matrix, then too bad, right? You actually have to solve the full eigenvalue problem. Now, another useful form of the quantum eigenvalue problem is actually in terms of the density operator rho. I just rewrite the first problem in terms of this PSD matrix, where trace rho equals 1. So suppose there's no degeneracy in the ground state eigenvalue, then this rho will actually become rank 1, and then the rank 1 component is really just your psi. Okay. All right. Okay. So now I just want to tell you again, right? These two problems really look similar. So all I did is I take this measure mu, I promote it to a density operator rho, okay? A function to an operator. Non-negativity constraint becomes PSD constraint. And then integration of 1 becomes, integration mu equals to 1 constraint becomes trace rho equals to 1 constraint, okay? They look almost exactly the same, except you change from function to operator, okay? So, and then let's just use the almost exactly the same method, okay? Right, so say we have some one variable basis, like a phi ji xi. Again, xi is indicating the dimension, ji is the number of bases is an index for the basis per dimension. So this one variable basis, I'm gonna promote it to a one-side operator. Okay, again, function to an operator. So what does it mean by a one-side operator? We're gonna start with some 2x2 operator, right? OJI tilde, right? This is a 2x2 matrix. I'm gonna take it and tensor product with a bunch of identity of 2x2 identity. And I'm gonna place this O tilde JI on the ith side. Okay. So this guy, right, OIJI, is the analog of the one variable basis in the quantum mechanical setting. Now, once I've defined my one variable basis, let me form the vector of my one variable basis, right? This is the vector of operator, and I'm going to define again my cluster moment. Okay, so M1 is really taking my density operator, integrate against B. And M2, right, second moment, is taking the density operator, integrate BB star. Okay. So, and these are the size of the moments, right? The first moment is just D times N, number of guys. And then the second moment is Dn by Dn. Okay. Right. So now I'm going to write my problems in terms of M1, M2. And again, I'm just going to enforce some necessary conditions that M1, M2 are moments of the density operator. And again, you have this PSD-ness constraint. So let me run this quickly through a concrete example, the transverse field Ising model. Okay. So let me start with some 2x2 one-side operators, the Pauli matrices. Okay. I'm going to insert one of these matrix on the I side and tensor product with a bunch of 2x2 identity. This is my one-side spin operator. Okay. Sigma I alpha. So the transverse field Ising model, right? Studied by Lipschitz Magnus in 1961, looks like this, right? So here you have the one-side operator, sum of one-side operator, and you have sum of two-side operator. So instead of having a polynomial of monomials, right? In terms of the monomials, you have a polynomial of operators. That's really how you should think about this. Now, okay, when the magnetic field is 0, this Hamiltonian H is actually diagonal. So if you look at sigma IZ, right? Sigma Z is like 1 minus 1. So a bunch of tensor product with 1 minus 1 is still a diagonal matrix. So if H equals to 0, this is called the magnetic field. H is a diagonal matrix. So like I said, this is going to boil down to something classical, right? Like if you have a diagonal Hamiltonian, you actually retrieve the max cut SDP if you have H equals to 0. So in this case, you have this term being 0. All you need to do is you need to care about the moment of sigma IZ, sigma JZ over here, this guy. Okay. So well, in this case, you're gonna get back to some D by D matrix. And then you have this condition, right? If you look at the moments of sigma IZ times sigma IZ star, sigma IZ is a diagonal matrix 1 minus 1. It multiplied by itself, it gives you identity. So this integration gives you something like, gives you 1, okay? Well, now you have a max cut type SDP. You have a linear equation in terms of the second moment, and the diagonal of the second moment has to be 1, okay? So often when you try to solve this, the solution is rank 1, okay? Or not very high rank. So you can use things like low rank SDP solvers to speed it up. And the per iteration complexity is going to be order D, okay, linear in the dimension T. Well, however, things are not very nice in the quantum mechanical setting where this magnetic field H is not equal to 0. Okay? So in this case, I further need to bring into sigma X and sigma Y, right? So in a quantum mechanical setting, you have to kind of consider a spin in a three-dimensional space. It points in X, Y, Z direction instead of the classical case where it only points in +1 and -1. So once you bring this into the picture, right, like well, I'm gonna form my moment vector, right? Well, my operator vector in terms of all sigma I X, Y, Z. And then now my first moment is gonna be 3D. Second moment is gonna be 3D by 3D. Okay. So again, the 3 comes from the fact that I'm considering spin in X, Y, Z direction. And I have D spin. Okay. So 3D by 3D. And there are many, many more constraints on this, not just a diagonal constraint. In fact, you have D squared number of constraints. So the number of constraints is as big as the number of variables. Okay, so now we have this positive definite constraint. So in the end of the day, we're gonna solve this standard STP problem. You have a cost for the energy, and then you have some constraints while saying that these are quantum mechanical spin moment, okay? And then you have a positive semi-definite constraint. Or actually, it's more fruitful to look at the dual problem for this, okay? So this is a dual problem. Lambda is a dual variable to the equality constraint. S is a dual variable to the moment positive semi-definite constraint. And you have the stationary equation, first order stationary equation. Okay, so the challenge of the quantum mechanical setting is that there's no low rankness, okay? So when the magnetic field is non-zero, in general, the rank of M is large, okay? This is really trying to capture quantum effect. So the ground state of a quantum system, unlike the ground state of a classical system, has actually non-trivial correlation. This is what giving rise to quantum phase transition and all this stuff. So in the worst case, the iteration complexity can be ODQ, because in order to ensure the positive semi-definiteness, you have to do an SVD, right? It's going to be expensive. And our approach is to appeal to structure matrices. And yeah, again, it's a pioneered by Vladimir. And yes, I hope that's a correct acknowledgement. Yes. And then, we're going to try to represent our matrices as like sparse low rank or hierarchically low rank matrices in the optimization problem. In this case, the algebra can be done in near linear time complexity. Okay. All right. Say we want to solve the dual problem. Okay, this is the dual problem, and we're going to use the augmented Lagrangian method for the dual. Okay. So this is the type of approach that adopted by SDP and AL plus for large scale SDP. You start with a dual problem and you use augmented Lagrangian method to solve it. Okay. So here again, this is the Lagrangian and this is the augmented part. I'm using a square to penalize the constraint. Okay. So as you can see, to do this, at least I need to be able to perform inner product quickly, and I need to be able to impose the positive semi-definite constraint quickly. Okay, so these are basically the requirement. Now I'm gonna perform some reparametrization. So C is the Ising interaction matrix. It's generally sparse. It's usually 3-point stencil or 5-point stencil. Then N is my moment matrix. I'm gonna impose hierarchically low rank structure on it. And S is the dual variable to the moment matrix. It has to be positive semi-definite. We're gonna make it hierarchically low rank and make it furthermore, I'm gonna make it positive semi-definite by paying a little bit more price. Okay. Now the last part, right? A star lambda. You can look at the first equation, right? If I have everything in terms of structure matrix, C is a structure matrix, S is a structure matrix, this guy is also going to be a structure matrix. Okay, so A star lambda is going to be a structure matrix. Okay. All right. So if I have all of this satisfied, then I can evaluate this loss function in actually d log d time. Okay. But is it possible? Okay. So first I will look at the first I'll look at the moment matrix. Okay, so I'm going to use the fact that there is a decay of correlation. So here's a celebrated theorem in quantum physics by Hastings and Coma. It's rather recent. So for a Hamiltonian H, right, where the interaction term is defined on a 1D lattice. So if there's a spectral gap between the first and second lowest eigenvalue of the H of H, then you have a decay of correlation, meaning, right, you compute the second moment, right? So this is a correlation between OI and OJ, and I subtract out the mean, right? So this is the mean part, I multiply together, and it's going to decay exponentially fast as a separation of dimension I, dimension J. And there are more general cases that you can handle. Basically, for example, this paper generalize such a theorem to a more general interaction graph. Basically, you have an interaction graph defined on a graph where the graph is kind of like is nearsighted. Okay, the interaction is nearsighted. Okay, so in this case, if you look at this factorization, you know that the off-diagonal part of the second moment matrix is actually low rank, right? This is actually saying that the second moment is a rank 1 factorization for the off-diagonal part. Now, pictorially, it looks like the following, right? So this guy is low rank, and you further partition it, this is low rank, and then in the end, you have the diagonal matrix. Okay. Now, if you have that, you can do matrix-matrix multiplication in d log d time. So what we didn't manage to show is that the dual matrix actually also has this type of a hierarchically low rank structure. So again, right, like unlike M, right, this dual matrix S has a positive semi-definite requirement. So I cannot just use this type of factorization to handle it, because this type of factorization is not guaranteed to be positive semi-definite. So what I'll do is I'm gonna pay a little bit of price of over parameterization. So I'm gonna start with S being a low rank matrix, right? Y1 star, and then I'm gonna move to a diagonal. I'm gonna create a low rank matrix on the diagonal. Then I'm gonna move towards the smaller diagonal, and I'm gonna create a lower rank matrix on the diagonal. So in this case, every piece of them is a positive semi-definite matrix, and you add them together, it's still positive semi-definite. Again, you have OD log D parameters, and the matrix multiplication is a little bit more pricey. It's a D log square D. Okay. So I don't really have a theorem to guarantee that the dual matrix of the moment matrix is actually positive. Well, we actually have this positive semi-definite hierarchical structure, but I'm going to show you a picture of how it looks like. So this is really the matrix. As you can see, the edges are really concentrated on the diagonal, and over here is pretty empty. Okay. So here I'm providing some fit error to some small matrix where I can compute it very faithfully. So that type of fitting, like it provides me like 10 to the minus 4 relative error using that type of parameterization. Okay. Okay, so in the end of the day, so I'm going to show you some numerical results for spin system of a different size in 1D. So here, I'm actually going to set my magnetic field at the phase transition point. So this is actually the hardest point of the problem, where the rank is going to be the largest. Okay. And so if I only parameterize my dual matrix as a hierarchical matrix, in this case, I'm not going to leverage the full advantage of structure matrix. I'll have to pay the price of OD squared complexity, but this is still better than ODQ. And I can solve a spin system from 256 all the way to 4,000. And the size of the PSD matrix is actually 4,000 times 3. So it's actually almost 15,000. Okay, 12,000 by 12,000. And this is the type of accuracy that I'm getting when I compare it to the ground truth energy. So this is at the phase transition point. I'm getting the worst error is 3%. But if you're away from the phase transition point, you get like sometimes 3 digits. If I have both the primal moment matrix and the dual moment matrix in terms of hierarchical matrix, then I get this type of complexity, this nearly near time. Somehow the optimization problem becomes harder. I can only solve it up to 2,000 due to the non-convexity injected by this reparameterization. But still, like if I can solve it, I can make it 3% error even in the hardest case. Well, thanks a lot for listening. And yeah, that's it. Yeah. Oh, H equals to 1. So so this is kind of like you can think about it. So you can think about this H in the quantum mechanical setting as the temperature in the classical Ising model. So if H equals to 0, it's kind of like a temperature 0 case of the Ising model, like of the classical Ising model. So if you change the temperature to a certain point, suddenly so the spins would like to orient in a certain direction. So it's called like a quantum phase transition. Yeah.
Is your model one-dimensional?
It's one-dimensional so far.
But why it has phase transition.
Oh yeah, one-dimensionalizing transverse Ising model actually has a phase transition.
It has.
It has this phase transition. Yeah, this is not like classical Ising model where it doesn't have a phase transition. Yeah.
So the model you show, is that the Heisenberg model?
Yeah, you can think about it as a more restrictive setting of the Heisenberg model. Yeah. Yeah. This is the.
I could be wrong, but only Heisenberg model has an analytic solution.
It has an analytic solution. That's why we can compare with the ground truth energy.
Okay.
Yeah. Yeah. Otherwise, there. Yeah. I can show you some number, but that number wouldn't mean anything. Yeah.
There's no more questions? Yes. Can you all speak again?